डॉक्टर ज्योति थोरात, महात्मा फुले महाविद्यालय, डिपार्टमेंट ऑफ केमिस्ट्री. Okay, see the name of the topic ionic solids class D by BSc. Has a definite and regular arrangements of atoms, ions or molecules in three-dimensional space. Then see the some definition here. First definition, crystal lattice. Crystal lattice, that is the definite and ordered arrangement of the constituent extended over a large distance in the crystal. This is called crystal lattice. Next, points. The position of atoms, ions or molecules in a crystal relative to one another in space are designated by points. Next, lattice. The lattice may be defined as an infinite set of points repeated regularly through the space. A lattice is classified in three ways. First, one-dimensional lattice, two-dimensional lattice and three-dimensional lattice. Then you have seen the one-dimensional lattice. A set of points repeated at regular interval along a line, that is one-dimensional lattice. Second, two-dimensional lattice, where a set of the points are repeated along any two coordinate axis, that is two-dimensional lattice. Three-dimensional lattice, the points in a two-dimensional lattice can be extended in three-dimensional, that is the three-dimensional lattice. Then see the unit cell. What is meant by unit cell? See the definition. A unit cell is the smallest building unit of the crystal. Or a unit cell is the smallest replacing unit in space lattice which when repeated over and over again. See the types of the unit cell. There are the three types of the unit cell which is based on the cube. See the first, a simple cubic unit cell in which the atoms are placed one at each corner. See the figure, that is the first simple cubic unit cell. Second, a body-centered cubic cell in which there is an atom at each corner and another at the center of the cube, that is the second figure. Third, a face-centered cubic unit cell in which there is an atom at each corner and one in the center of each face of the cube. See the third figure, that is face-centered cubic unit cell. Next, close packing. See what is the close packing? The arrangement of the maximum number of ions or atoms into the smallest possible space is called close packing. In such arrangement, each sphere is in contact with maximum number of nearest neighbors, which called the coordination number of the sphere. With close packed arrangement, the spheres occupy 74% of the total space. See for the example, hexagonal closest packing. Second, cubic closed packing. See the first hexagonal closed packing. There are always 6 balls or spheres arranged in the shape of the hexagon around a ball or sphere in the center of the hexagon. This type of arrangement is called hexagonal close packing. See in the figure, these layers are each other to the each other here. That is the A hexagonal packed arrangement. Then second, cubic close packing. In this type, the balls or spheres of the third layer are placed above the gaps in the first layer. Hence, the second layer covers half the holes in the first layer and third layer lies of the remaining holes. See in the figure, that is the first layer, second layer and third layer are each other here. Hence, the crystal layers are more precisely called face-centered cubic. Next, that is see what is the voids or holes in closed packed structure. In any layer of closed packed arrangement of spheres, the unoccupied value is called void or hole. Types of the holes. First, tetrahedral holes. These holes are surrounded by 4 spheres. That is, the coordination number of tetrahedral hole is 4 and the hole is marked by the letter capital C. See that the figure, that is the tetrahedral hole, is also marked by the letter P. Then second type, octahedral holes. These holes are surrounded by 6 spheres. That is, the coordination number of octahedral hole is 6 and that hole is marked by the letter O. See in the figure, that is the octahedral hole and it is marked by the letter O. Next, we have seen the structure of ionic compounds. In the structure of ionic solids, there is alternate arrangements of cations and anions. The common stable arrangement of ions gives tetrahedral, octahedral and cubic arrangement of ions around the central ion. See the types of ionic crystal structure. Ionic compounds are divided into 2 groups, that is Ca and Ca2. C for cation, A for anion. See the first type, that is Ca type. Ca type, the examples are sodium chloride, caesium chloride and sulphide. Second type, that is Ca2 type, the example are calcium chloride. See the first structure here, that is sodium chloride structure. The silent feature of this structure is as follows. First, it has face-centered cubic structure. Second, the radius ratio useful in predicting the type of crystal structure. Third, the radius of sodium ion is 0.96 angstrom unit and that of Cl minus ion is 1.81 angstrom unit. To calculate the radius ratio of sodium chloride by using the formula, the radius ratio is equal to radius of sodium ion divided by radius of chloride ion, that is 0.96 divided by 1.81. The value is 0.525. That value suggests that it gives the octahedral arrangements of the ions in the crystal structure. That is, each sodium ion is surrounded by 6 chloride ions at the corners of the regular octahedron, and similarly each Cl ion is surrounded by 6 sodium ions. The combination number of sodium ion as well as the chloride ion is 6. In this case, positive and negative ions are alternatively arranged. See in the figure, that figure you have seen. Then see, the sodium chloride structure is a common type and it is known as the rock salt structure. See in the figure, that is each sodium ion. In this figure, the central is sodium ion and Cl ions are found at the 8 corners of the cube and also corner of the each unit cell. This arrangement of the ions in the crystal lattice is called as the face-centered cubic structure, caesium chloride structure. The silent feature of this structure as follows. The radius of caesium ion 1.69 angstrom unit. The radius of chloride ion 1.81 angstrom unit. Calculate the radius ratio of caesium chloride. Radius of caesium ion divided by radius of chloride ion, that is 1.69 divided by 1.81. The value is 0.93. That value suggests that the value is close to the 1. The coordination number be 8 and it should be have cubic structure. It can be considered that caesium chloride structure is caesium ion occupies, see the structure, center of the cube, and chloride ion is also occupied, that is the center of the cube, and 8 caesium ion is surrounded by, that is the corner of the cube. The structure is also described as the body centered cubic, but this would be misnomer because the body centered cubic structure is one which has the same atoms at the body center as well as the corners. Then see, whereas the caesium chloride structure, the ions is the body center and corners are different. It must be described as body centered cubic type of arrangement rather than body centered cubic. Next structure, zinc sulphide structure. Then here there are two types of the zinc sulphide structure. First, zinc blende structure. Second, wurtzite structure. Zinc blende structure. Calculate the radius ratio of zinc blende structure. Radius of zinc ion divided by radius of sulphide ion. The value is 0.40. This suggests that the coordination number is 4. In this structure, see the structure. In this structure, the sulphide ions are arranged in cubic closed triangle arrangement, that is at the corners of the cube and at the center of each face. The zinc ions occupy half the tetrahedral side. Since there are two tetrahedral sides per atom in closed triangular lattice. In arrangement, only half of the tetrahedral sides are occupied by zinc ions, so that each sulphide ion has one zinc ion. Therefore, the stoichiometry of the compound is 1:1. See the zinc blende structure. Next, wurtzite structure. The wurtzite structure may be described as follows. The sulphides ions are arranged in a hexagonal closed triangle arrangement. The zinc ions occupy half of the tetrahedral side. There are, see the structure. This is the structure of the wurtzite structure. The zinc ions occupy half of the tetrahedral side. There are two tetrahedral sides of each sulphide ion in the lattice. Since only half of them are occupied by zinc ions, each sulphide ion is surrounded by 4 zinc ions which are disposed towards the regular corners, disposed over the corners of the regular tetrahedron. Similarly, each zinc ion is surrounded by 4 sulphide ions. Therefore, the coordination number of zinc ion and sulphide ion is wurtzite structure are 4:4. The radius ratio of this structure 0.40, which suggests that the coordination number is 4 and that of the crystal has a tetrahedral structure. It will be noted that the basic difference of chin plate, and one-side structure is that, whereas in the former case, the sulphide ions are orange in CC type. In the latter case, they are orange in the SCP type of the packet. That is the difference between chin plate and one-side structure. Next, second type C, the crystal of the type Ca2. An example, C, the structure of calcium chloride. The silent feature of that crystal is given as below. The calcium ions are orange in CCP, that is cubic close packing arrangement, so that there are calcium ions at all the corners and at the center of each face of the tube. The chloride ions occupy all the tetrahedral sites seen in the figure. Since there are two tetrahedral sites for each calcium ions and chloride ions occupy all the tetrahedral sites, there will be the two chloride ions for each calcium ion seen in the figure. In this arrangement, each chloride ion is surrounded by 4 calcium ions, whereas each calcium ion is surrounded by 8 chloride ions in the figure. The coordination number of calcium and chloride ions are 8 and